From the vast cosmos to our own bodies, the universe is a realm of endless wonder. Classical physics described the motion of planets and the flow of heat, but deeper exploration revealed phenomena beyond its reach. This new realm, where energy is quantized and particles exhibit wave-like properties, is the domain of quantum physics. The quantum revolution had begun. The quantum revolution was a gradual transformation driven by groundbreaking discoveries. Max Planck proposed that energy exists in discrete packets, explaining blackbody radiation. Albert Einstein extended this idea to explain the photoelectric effect, earning him the Nobel Prize. This work highlighted the dual nature of light, central to quantum mechanics. The quantum revolution attracted brilliant minds like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. In the quantum realm, superposition challenges our classical intuition. Particles can exist in multiple states simultaneously, defying either or thinking. In the quantum world, particles like electrons and photons exist in a superposition of states. This inherent uncertainty is a fundamental aspect of quantum systems. This concept has profound implications for our understanding of the universe. Imagine a quantum coin that exists in a superposition of both heads and tails simultaneously. It embodies both possibilities at the same time, existing in a probabilistic state. Only when we measure the state does it collapse into a single, definite state. This interplay between superposition and measurement is key to quantum mechanics. Superposition governs all quantum systems, from subatomic particles to atoms and molecules. Electrons can exist in a superposition of energy levels within an atom. Photons can exist in a superposition of polarization states until measured. Entanglement reveals a profound interconnectedness between particles. Two particles linked in such a way that knowing the state of one instantly reveals the state of the other. In the quantum realm, entanglement allows particles to be linked non-locally. Measuring one entangled particle determines the state of its partner regardless of distance. This connection has been experimentally verified, confirming the reality of entanglement. Imagine a pair of gloves, one left and one right, sent to two different friends. When one friend finds a right glove, they instantly know the other has the left glove. In the quantum world, the gloves exist in a superposition of both states until observed. This instantaneous correlation is what makes entanglement remarkable. Entanglement seems to violate locality, where an object is influenced by its immediate surroundings. Some interpretations suggest hidden variables, while others propose fundamental non-locality. Experimental verification of entanglement has profound implications for our understanding of reality. The universe is more interconnected than we previously imagined. The journey into the quantum realm was a collaborative expedition by brilliant minds. Max Planck's work on blackbody radiation ignited the quantum revolution. Planck proposed that energy is emitted and absorbed in discrete packets, or quanta. Albert Einstein extended Planck's hypothesis to explain the photoelectric effect, earning the Nobel Prize. These early breakthroughs laid the foundation for a new generation of physicists. The stage was set for a comprehensive theory of quantum phenomena. The development of quantum mechanics was a tapestry woven from numerous contributions. Niels Bohr proposed the model of the atom with quantist energy levels. Werner Heisenberg formulated the uncertainty principle, a cornerstone of quantum mechanics. Erwin Schrödinger's wave equation described the wave-like behavior of quantum particles. These contributions continue to challenge our understanding of the universe. Quantum mechanics forced physicists to confront fundamental questions about reality. Heisenberg's uncertainty principle challenged the deterministic worldview of classical physics. Niels Bohr's principle of complementarity proposed wave-particle duality. Quantum mechanics has had a profound impact on our philosophical understanding of the universe. Despite its strangeness, it has proven to be an incredibly successful theory. Quantum mechanics remained theoretical for much of the 20th century. Today we stand on the cusp of a new technological era driven by quantum technologies. Quantum technologies leverage principles like superposition and entanglement. These technologies promise to revolutionize fields from computing to medicine. The future of quantum technologies is brighter than ever. Section 2. Computing power, the quantum leap. One of the most highly anticipated applications of quantum mechanics lies in the realm of computing. Quantum computers, unlike their classical counterparts that rely on bits representing either 0 or 1, leverage the principle of superposition to process information in a fundamentally different way. Quantum bits, or qubits, can exist in a superposition of both 0 and 1 simultaneously, allowing quantum computers to perform computations on multiple possible values at once. This inherent parallelism gives quantum computers the potential to outperform classical computers exponentially for certain computational tasks. While still in their early stages of development, quantum computers have already shown promise in areas such as drug discovery, materials science, and cryptography. For instance, quantum computers could be used to simulate the behavior of molecules with unprecedented accuracy, accelerating the development of new drugs and materials with tailored properties. Furthermore, quantum computers pose a significant challenge to modern cryptography, which relies on the difficulty of factoring large numbers, a task that would take classical computers an impractical amount of time. Quantum computers, with their inherent speed advantage for certain algorithms, could potentially crack these codes, necessitating the development of new quantum-resistant encryption methods. Quantum cryptography, another promising application of quantum mechanics, offers a way to secure communications by exploiting the principles of superposition and entanglement. Quantum key distribution protocols allow two parties to share a secret key that can be used to encrypt and decrypt messages with unparalleled security. Any attempt to eavesdrop on the communication would inevitably disturb the delicate quantum states, alerting the legitimate users to the intrusion. The development of practical QKD systems is an active area of research with the potential to revolutionize secure communication in various sectors including finance, government, and healthcare. Beyond cryptography, quantum technologies are also making their mark in the field of medicine. Magnetic resonance imaging, a widely used medical imaging technique, relies on the quantum properties of atomic nuclei to generate detailed images of internal organs and tissues. Emerging quantum sensing technologies promise to further enhance medical diagnostics and treatment. For instance, quantum sensors could be used to detect minute changes in magnetic fields, enabling the development of highly sensitive brain imaging techniques and potentially aiding in the early diagnosis of neurological disorders. The applications of quantum mechanics in medicine are vast and still being explored, offering the potential to revolutionize healthcare and improve human lives. Quantum physics, with its counterintuitive concepts, has often been shrouded in mystery and misconception. From science fiction to sensationalized headlines, the true essence of quantum mechanics can become lost. Quantum technologies are rapidly emerging, revolutionizing fields from computing to medicine. Demystifying quantum physics requires separating science from speculation. It's a journey of exploration and discovery, bringing us closer to comprehending reality. The allure of misinterpretations surrounding quantum mechanics stems partly from our human tendency to seek familiar patterns and explanations, even in the face of phenomena that challenge our classical intuitions. We often try to fit the strange and counterintuitive world of quantum mechanics into our existing worldview, leading to misconceptions and misinterpretations. For instance, the concept of quantum entanglement, with its seemingly instantaneous connection between distant particles, has been used to justify various pseudoscientific claims, from telepathy and ESP to the power of human consciousness to influence the physical world. It's crucial to approach such claims with a healthy dose of skepticism, separating legitimate scientific inquiry from unfounded speculation. While quantum mechanics undoubtedly has profound implications for our understanding of the universe, it's essential to remember that correlation does not equal causation. Just because two events are correlated, even in a seemingly spooky way, doesn't necessarily mean that one event causes the other. Furthermore, The language we use to describe quantum phenomena can sometimes contribute to misunderstandings. Terms like observer, measurement, and collapse can carry connotations from our everyday experience that don't necessarily translate accurately to the quantum realm. It's essential to remember that these terms have specific definitions within the context of quantum mechanics and shouldn't be interpreted literally. Embracing the quantum reality requires a shift in perspective, a willingness to let go of our classical biases and embrace a new way of understanding the universe. It means accepting that the universe, at its most fundamental level, is inherently probabilistic, that particles can exist in a superposition of states, and that entanglement can link distant objects in ways that defy our classical intuitions. It means acknowledging that our observations can influence the systems we observe and that the act of measurement plays a crucial role in shaping quantum reality. This doesn't mean abandoning our classical understanding of the world entirely. Classical physics still provides an accurate description of the macroscopic world we experience daily. However, it's essential to recognize that classical physics is an approximation, a limiting case of the more fundamental framework provided by quantum mechanics. Just as Newtonian mechanics gave way to Einstein's relativity at high speeds and strong gravitational fields, so too does classical physics give way to quantum mechanics at the atomic and subatomic levels. Embracing the quantum reality is not about discarding our classical intuitions, but rather about expanding our horizons, accepting that the universe is far stranger and more wondrous than we could have ever imagined. It's about embracing the unknown, acknowledging the limitations of our current knowledge, and approaching the quantum world with a sense of curiosity and wonder. As we draw the curtains on our exploration of quantum physics for beginners, it's important to remember that this journey is far from over. The quantum world, with all its strangeness and wonder, remains an active frontier of scientific inquiry, a symphony of discovery still being composed. What we've uncovered so far, from the mind-bending concepts of superposition and entanglement to the transformative potential of quantum technologies, is but a prelude to a grander composition, a masterpiece still being written by physicists worldwide. One of the most profound implications of quantum physics is the realization that the universe is not a collection of isolated objects, but rather a deeply interconnected web of relationships. From the smallest subatomic particles to the largest cosmic structures, everything in the universe is linked in ways we are only beginning to comprehend. The concept of entanglement, once considered a bizarre and fringe idea, has now taken center stage in our understanding of the universe. It suggests that the universe is far more holistic and interconnected than our classical intuitions might suggest. This interconnectedness is not merely a theoretical curiosity, it has profound implications for our understanding of the nature of reality itself. The classical worldview, with its emphasis on separateness and objectivity, is giving way to a more holistic perspective, where the observer and the observed are inextricably intertwined. The act of observation, once considered a passive process of recording information, is now recognized as an active participant in shaping quantum reality. This shift in perspective, from a universe of separate objects to a universe of interconnected relationships, has the potential to revolutionize not only our scientific understanding but also our philosophical and spiritual views. It invites us to reconsider our place in the grand tapestry of the cosmos, to recognize our interconnectedness with all things, and to approach the universe with a renewed sense of awe and wonder. As we conclude our exploration of quantum physics, let us carry with us a sense of excitement for the journey ahead. The quantum world, with its endless possibilities and profound mysteries, beckons us to explore and marvel at the elegance and strangeness of the universe. The quest for understanding is an ongoing dance, a balance between embracing the unknown and seeking answers. As we probe the quantum realm, new and astonishing discoveries await us, challenging our understanding. Let us embrace the quantum dance, with all its uncertainties and exhilarating possibilities.